while discussing these. So let's go back to the discussion about cyclic processes and see how cyclic processes can be classified into two categories: heat engine cycles and reverse heat engine cycles. So we've already seen the application of cyclic processes in context of application of first law. In fact, in yesterday's lecture also we saw it in a couple of questions as doubts. But now let's understand the proper terminology and the various physical quantities related to a heat engine cycle and a refrigeration cycle. And of course, you would have heard of the important category of heat engine called the Carnot cycle or the Carnot engine. So we will look at that also at the derivation of the formula for efficiency of Carnot cycle. So first of all, going back to cyclic processes. Okay, so we have already understood the general application of first law in a cyclic process, that the net heat exchange during the cycle is equal to the net work done by the gas during the cycle, because obviously the state function, which is the change in internal energy during the cyclic process, is zero. Okay. So now we see that based on this, there are two categories of cyclic processes. If Q in the cycle equal to W in the cycle is a negative quantity, that means heat is withdrawn from the gas and work is done on the gas during the cyclic process.
The swoosh will be.
So such a process is categorized as a refrigeration cycle. Okay. Or also a reverse heat engine cycle. So this type of a process on the PV space, as we've discussed earlier, will look like an anti-clockwise loop, because Q net is negative and net work done during the cycle is negative. So any loop which runs anti-clockwise in the PV space is an example of this. So net heat is withdrawn from the gas and work is done on the gas. That is why it is called a refrigeration cycle, because heat is extracted and work is done on the system. Whereas on the other hand, if these two are positive quantities, then we are referring to a clockwise loop in the PV space. And in that situation, what is happening is heat is supplied to the gas and work is done by the gas during the cycle. So that becomes what is called a heat engine cycle, because heat is supplied to extract work from the gas. Here, work is done on the gas to extract heat in working principle or in function. So any process that involves a compressor, whether it's a refrigerator's compressor or an air conditioner's compressor, it involves a refrigeration cycle or a reverse heat engine cycle. So an everyday practical physics example of something that functions on a refrigeration cycle is the process of a compressor. Okay. So it is used to extract heat from a system, okay, by supplying mechanical energy. to it. In other words, by doing work on it. So electrical energy is converted into mechanical energy, which is the work done on the system by the compressor. And in exchange for that work done, heat is extracted from the system. So that is the functioning of the general functioning of a reverse heat engine or a refrigeration cycle. Okay, next up.
Excuse me. So can you please scroll it up?
Sir, can you please scroll it up?
Yes, I've scrolled it up only. Right? The heading is there before that, which is cyclic processes.
Done, sir.
Done.
Okay. So the second type of cyclic process is just the opposite of this. That's a clockwise loop. So if the net heat exchange during the cycle equal to the net work done during the cycle is a positive quantity. So then that means basically what is happening is work is done on the gas. Sorry, work is done by the gas and heat is supplied to it. So heat is supplied to the gas, and in exchange work is done by it. So this is what is called a heat engine cycle. So an everyday example of it is the internal combustion engine. Okay. So in the internal combustion engine, heat from combustion or burning of fuel, of any type of fossil fuel, is supplied and mechanical energy is extracted from it or work is done by it. So such a process, as you know, in the PV cycle or in the PV space, it will look like a clockwise oriented cyclic process, or look like a clockwise loop. So whatever the shape of the loop, it will be running clockwise. Okay. So heat is supplied to the gas and mechanical work is extracted from it. So that is the function of a heat engine. So yesterday we've already seen a couple of examples of numerical problems related to this calculation of the net heat or the net work done during the cycle. And in fact, we had seen some examples where the cycle was given to us in terms of the temperature volume relationship and how we converted it into the pressure volume relationship. And from that, we calculated the terms of the first law. Now, today we'll look at a more detailed view at the individual processes that go on to make the cycle of a heat engine or of a reverse heat engine, and certain physical parameters related to those internal processes within the heat engine or within the refrigerator cycle. Okay, so let's look at the working of a heat engine in more detail. So the general working principle of a heat engine. Okay. So heat engine in general is defined as a device running on a cyclic process. Okay, repeated indefinitely, such that heat supplied is converted
Sir,
into,
can you scroll up?
okay, let me finish writing this one, into mechanical work. So that is the function of a heat engine. Okay. Now the general working principle of any heat engine, or you can say the general schematic of a heat engine, it is based on three principal processes which are taking place and three parts of the cycle. So every heat engine will have something called a heat source. So in the case of internal combustion engine, for example, the heat source is the combustion process that takes place of fuel in the cylinder of the internal combustion engine. You must have heard the term cylinder of the engine, 4-cylinder engines, 6-cylinder engines, 12-cylinder engines. So in each of these cylinders individually, there is combustion of fuel taking place, and that combustion of fuel is the heat source for the engine. And there is another part of it which is, so this is the cyclic process. Another part of it which is called the heat sink. So some part of the heat which is absorbed from the heat source is always dissipated into the heat sink, but the remaining of it is converted into mechanical work. So if Q1 and Q2, they denote these quantities. Q1 is the heat supplied by the heat source during one cycle, okay, of the heat engine. During completion of one cycle, that cyclic process, Q1 is the amount of heat that is supplied by the heat source. Okay. Q2 is the amount of heat dissipated into the heat sink. Okay. So in any practical process, this dissipation of energy is inevitable. We cannot design an engine in which all the heat that we are supplying from the source will be converted into 100% work. Some part of it will unfortunately always get dissipated. For example, in the case of the internal combustion engine, it is the heat coming out of the exhaust gases, which is the process of the heat sink. Okay. So this is part of what we call second law of thermodynamics, that we cannot design a heat engine where 100% of heat supplied by the source is converted into mechanical work. There will always be a certain percentage of heat supplied from the source which is dissipated into the heat sink, which cannot be recovered or which cannot be converted into mechanical work. So this is Q2 is the amount of heat dissipated into the heat sink during one cycle of the engine's operation. And W is the net work done by the engine during one cycle. So you can also say that that work done is equal to the mechanical energy generated by the engine per cycle. So every time the engine goes through one cycle of its process, this thing is repeating. Q1 amount of heat is extracted from the source and supplied to the engine. W amount of mechanical energy or work done by the engine is extracted from it, and certain percentage of that Q1 supplied gets dissipated into the heat sink, and that is Q2. Okay, so therefore
Sir,
Q for the cycle, yes.
Sir, remaining with upper part.
What happened, beta? Please speak a little louder. Yes. Not able to hear you people.
Sorry, saying
Yeah,
that
Prince had.
that upper part he hadn't noted down.
Okay, I'll take you back to that. Let's finish this first. So the net heat supplied to the cycle or to the engine during one cycle, that is Q1 minus Q2. Whereas the net work done during one cycle is equal to W. So since Q cycle is equal to W cycle, we have the equation that Q1 minus Q2 is equal to W. So this is the first important relationship between the physical parameters of the heat engine cycle. That if you are extracting Q1 amount of heat from the heat source and Q2 out of that is getting dissipated, then Q1 minus Q2 is the net heat supplied during one cycle. So it's Q cycle. And that is equal to the net work done by the loop during one cycle. So that is equal to W cycle or W. Okay, so just make a, we'll like here finish writing this down, then we'll come to the lower part again.
Sir, done.
So completed.
Sir, scroll down. Sir, this one. Sir,
Yes, Prince, you have some doubt, beta?
no, sir.
Okay. Okay. Now, once you understood this basic working principle that
Effect of
Q1
natural
amount of heat is supplied from the source, just still not finished.
transfer.
Okay. So once you understood this, Q1 amount of heat is supplied from the source. Q2 amount of heat is dissipated into the sink. So the net heat exchange during the cycle is Q1 minus Q2. And the net work done is equal to W. So Q1 minus Q2 is W. Now we define the most important parameter for the engine, that is the efficiency of the heat engine. So the whole purpose of the cyclic process is to convert as much as possible of the heat supplied from the source, that is as much as possible of Q1 into mechanical work, that is W. So the efficiency of the process is defined as how efficient the engine is in converting the maximum possible part of Q1 into W. Okay, so efficiency mathematically therefore will be defined as the ratio of W by Q1. So efficiency of the heat engine is basically about, so it's denoted by the symbol eta. It's about what fraction of Q1, that is the heat supplied from the source, is converted into useful mechanical work, that is W. Okay. And if you combine equation 1 and 2, so it can also be related as Q1 minus Q2 by Q1, or the efficiency can also be expressed like this: 1 minus Q2 by Q1. That is the fraction of heat converted into mechanical work is also equal to 1 minus the fraction of heat dissipated divided by the heat supplied. So whether we use this formula or this formula, we're talking about the same quantity, which is the efficiency of the engine. And if we convert it into a percentage, then it is called the percentage efficiency. That is W by Q1 expressed as a percentage. So higher the percentage, the more efficient we can say the process is. So now one important thing here is that from the application of second law of thermodynamics, okay,
Sir,
yeah,
sir, in that percentage efficiency, 1 minus Q2 upon Q1 into 100 will come, no?
yes, that also is converted to a percentage. Yeah, so no heat engine can have 100% efficiency. Heat engines will always have an efficiency percentage of less than 100%. This is the statement of the second law of thermodynamics applied to heat engines. So this is the statement of second law as far as our physics syllabus is concerned. In chemistry, you might have heard of second law expressed in terms of entropy. That second law of thermodynamics is the law of entropy. It states that the universe is always increasing. But in our physics syllabus, that entropy part is not part of our course. And instead, the second law of thermodynamics is reduced to a statement which is applied to heat engines in particular. And that statement is this: that the efficiency of heat engines will always be less than 100%. No heat engine can have an efficiency of 100%. So let's look at a couple of examples of calculation of efficiency.
Sir, we have not copied it down.
Still not copied that part down. Okay. Hurry up, it. Okay. Be fast in copying.
Done, sir.
So let's look at our first example.
So 1 minute, sir. 1 minute. Sir, not. Sir, he has completed. We have. So,
Yes, completed.
sir, done. Thank you, sir.
Okay. 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 So let's look at our first example of calculation of efficiency of a given heat engine. So now let's say our heat engine or a cyclic process representing a heat engine is an extremely simple one. It's represented by a rectangle on the PV space. So for a given cyclic process like this, how to calculate the efficiency? Pressure versus volume. This is for a monoatomic gas going through a heat engine cycle. Say ABCDA. So given that pressure at A is 4 atmospheres or 400 kilopascals or 4 into 10 raised to 5 pascals. Okay. Volume at A is 2 liters and temperature at A is say 300 Kelvin. Temperature at B is 900 Kelvin and temperature at D, this one here, is 150 Kelvin. So we want to find, first of all, volume at B, okay, pressure at C, then we want to find out Q for the cycle ABCDA, okay, and we want to find out the percentage efficiency of this cyclic process. So this is quite simple, really, especially the first two parts are very similar to questions that we did yesterday. So just try this out. We'll discuss more. Okay, send me the answers for the first and second part. They're quite simple. Really. Okay, Yash Madani and Yash Bhaviskar both correct. Kshitij correct. Tej correct. Okay, so let's work this out quickly. So if we take this pressure as, let's say, P1, this pressure as P2. So this one's value we already know. This pressure is 4 atmosphere. Okay. This volume as V1. This one's value we already know. This is 2 liters. Okay. This volume is V2. And also we know this temperature is 300 Kelvin. This temperature is 900 Kelvin. Temperature is 150 Kelvin. Okay. So now we can find out all these things. This one, the temperature at point C, all these things we can find out. Okay. So we can see that dA is isochoric. Okay. So PA by PD should be equal to TA by TD. So this will tell me that the pressure at the point D should be 2 atmospheres. Okay. So this is coming out to be 2 atmospheres. Okay. Now similarly, AB is isobaric. So volume is proportional to temperature. So VB by VA should be equal to TB by TA. This will tell me that volume at V should be 3 times this because the temperature is 3 times. So this should be 6 liters. So this is coming out to be 6 liters. Okay. And then you can see the pressure is becoming half here. So this temperature TC should be half of TB. So this should be 450 Kelvin. Okay. So anyway, only these two things were asked, which we already found out. Now, Q for the cycle is very simple over here. Q for the cycle will be equal to W for the cycle, which will be positive of the area of loop ABCA. Sorry, ABCDA. So that is just the area of this rectangle. So it's as simple as that actually. So the area of the rectangle, you can see this is 2 to 6. So that is 4 liters. And this is 2 to 4. So that is 2 atmospheres. So 2 atmospheres into 4 liters. So this quantity is equal to plus 8 liter atmosphere. Or in this case, we'll write it as plus 800 joules because we are taking 4 atmospheres as 4 kilopascals. That means we are taking 1 atmosphere as 100 kilopascals or 10 raised power 5 pascals. Okay. Therefore, 1 liter atmosphere will be 100 joules. So good, most of you have got this correct. Okay. So hope you understood why we have taken it as 800 joules, because this 4 atmosphere is given to us as 400 kilopascals. Okay, that means we are using the approximate value. Anyhow, now let's look at the efficiency. So for the efficiency, we have to understand how much is Q1, because W net of the loop we have already got. So now what we understand is that during this cyclic process, heat is coming into the gas because it's a isobaric expansion. So QAB is NCP delta, which is a positive quantity. So heat is coming in. Okay. But during BC, heat is going out. BC is isoporic cooling. That will be negative because you can see temperature is dropping. Okay. Similarly, this is also a situation where heat is going out. So CD. So CD will also be one where Q will be negative because this is an isobaric compression now. Okay, so Q will be negative. But during DA, again, heat is supplied to the gas because temperature is increasing. So QDA will be positive. So overall, thinking in terms of the schematic of our engine, what is the net heat which is coming in from the source? This is equal to QAB plus QDA. Whereas how much heat is being dissipated, it will be magnitude of QBC plus QCD. And the rest is converted into mechanical power. So that W is W cycle, which is 800 joules that we just calculated. But Q1 is this, which you can see will be, sorry, DA. So this you can see will be NCP into this plus NCB into, okay. So since this was P2 and this was P1, so we can also write this as N into monoatomic gas, so 5/2R. Now further, this can be reduced to 5/2 times NR delta T. So during isobaric process, it will become like this. And this one during isoporic process become like this. Okay. So this was 4 atmosphere, this was 2 atmosphere, this was, how much was this now? 2 liters. This was 6 liters. This is in liter atmosphere. So our Q1 will come out to be so this will be 5 into 4 into 2, 10. So 40 plus this will be
6.
6. So 46 liter atmosphere. So 4,600 joules. Whereas Q2,
So even that will be same, right?
now when
Q1 will be equal to Q2, right?
no, why will Q1 be equal to Q2? Q1 minus Q2 is W, na? So the difference will be 800 joules, na?
Okay, all right. Okay.
So Q2 will be mod of this QBC plus QCA. These will be individually negative quantities. So when we calculate this, this is again that NCV TC minus TB, which is a negative quantity, plus NCP TD minus TA, sorry, TD minus TC. So this will again be a negative quantity, but we'll take mod of it. So this will become 3 by 2 into this volume into this, okay, plus 5 by 2 into this pressure into this volume difference. So this will become minus of 3 by 2 into this volume is, sorry, 6 liters.
Sir, why is it minus of 3 by 2?
Because P1 minus P2 will become a negative quantity. Just
Yeah.
coming to that.
Okay. All right.
And similarly, this will be minus of 5 by 2 into this pressure, which is 2 atmospheres, difference, which is 4 liters. Yes, but when we take the mod, we'll remove the minus sign. So this is coming out to be how much in liter atmosphere now?
20 minus 20
18
minus
plus,
80. 20.
So minus 38, right?
Yes, sir.
So this will come out to be 38 liter atmosphere. So that is 3,800 joules. So this just verifies that what we were talking about earlier, that W was W cycle, which was 800 joules. Okay, but W should also be equal to Q1 minus Q2, which is 4,600 minus 3,800.
Yes, sir. Got it.
But more importantly, now what about the efficiency? Efficiency is W by Q1, or that's the same thing as 1 minus Q2 by Q1. So that will come out to be 8 by 46, right? So that is 4 by 23. So that is the efficiency, or percentage efficiency is 4 by 23 into 100. So this is the efficiency of the heat engine. So this type of calculation also becomes important for cyclic processes now. So in the cyclic process, what becomes important is you should be able to identify that in which part of the individual processes of the cycle heat supplied is positive and which part the heat supplied is negative. So Q1 becomes the sum of the heat supplied in the parts which are positive, and Q2 becomes the mod of the sum of the heats which are withdrawn from the gas. So this analysis that we have done over here, this becomes very important, because without doing this, we don't understand how to find out Q1 and how to find out Q2. Why Q1 is equal to only for AB plus DA? Because out of the 4 processes, in these 2, heat supplied is positive. In the other 2, heat is being withdrawn. So that is part of Q2 actually.
Done, sir.
Okay, so this is a general example of application of the concept of efficiency and calculation of efficiency of heat engine.
Sir, just a minute.
Okay.
Only last part.
Okay.
Done, sir.
Okay. Now let's come to the specific type of heat engine. So you can always get a general question like this, where some kind of cyclic process, which is, clockwise in the PV space, is given to you, and you have to calculate the efficiency. That's one thing. Now, one very specific type of heat engine is called the Carnot cycle, as you know, and it has a specific formula for calculation of efficiency. So the Carnot cycle, or you can call it the Carnot engine, it consists of a cyclic process, which, as you might know from chemistry, consists of two isotherms and two adiabats. Right? So you form a closed loop in the PV space, which runs in the clockwise direction, consisting of four individual processes. The cycle is completed by four individual processes. Two of them are expansions, two of them are compressions, and they are namely, so let's say you start from this point, you expand the gas initially via an isothermal process. So EB is an isothermal, and let's say that is occurring at a temperature of T1. Okay. Now next you compress the gas again, but this time adiabatically. So the adiabatic process will depart from the isotherm like this. Okay. So BC is now an adiabatic expansion. And after these two expansions, your next two processes are compressions. So you follow BC with another compression, but this compression is isothermal again. This is at a temperature T2. So again isothermal, but this time a compression. And finally, you compress it to a point where you can come back to A via an adiabatic process. So dA is an adiabatic compression. So as you will remember that the formula for Q during an isothermal process is nRT, natural log of Vb by Va in this case. So it's a positive quantity, but QBC will be 0. And then again QCA will be nRT2, natural log of Vd by Vc. Sorry, this is not Ca, this is Cd. Because again, this is an isothermal compression. And this will be a negative quantity because Vd is less than Vc. And finally, QDA will be again 0 because this is adiabatic. Okay. So given that this consists of two isothermal processes, isothermal expansion involves positive heat, isothermal compression involves negative heat or heat absorption, and these two are adiabatic, so zero heat exchange. So our heat exchange with the source is happening like this, whereas our heat exchange with the sink is happening during this time. So the source and sink are operating at constant temperatures. So the heat source, it operates at constant temperature T2, sorry, T1 isothermally. Heat sink, this also operates at constant temperature. But obviously T2 is less than T1. Okay, so now our efficiency, which is W by Q1, can also be written as 1 minus Q2 by Q1. Now we are going to show that the efficiency is actually equal to 1 minus T2 by T1. There's a couple of more steps involved in showing this, improving this. Okay, that will actually come from this formula and this formula, because we can see Q1 is equal to nothing but QAB, whereas Q2 will be equal to mod of QCD. Why mod? Because QCD is a negative quantity, as you can see. Okay. So we'll be able to prove that this ratio of Q2 by Q1 is actually equal to T2 by T1, and that's why the efficiency is given by this formula. But remember that T1 and T2 are in kelvins. They should be expressed in the SI unit, Kelvin, and not in the CGS unit of degrees. Because in the definition of this thing, the work done or heat supplied during isothermal process. The work done or heat supplied during isothermal process is not T ln V final upon V initial. So that T must be in kelvins. Okay, so that's why this formula also 1 minus T2 by T1. T1 and T2 should be in kelvins. Just make a note of this part first.
Excuse me, sir.
Yes, Tej, to answer your question, yeah, coming to your doubt also, the Carnot engine is specifically this cyclic process. Okay, it is a heat engine cycle. Okay, of the following processes. It must consist of these: isothermal expansion followed by adiabatic expansion followed by isothermal compression and adiabatic compression. Okay. Was that the doubt, or you have something else, Tej? Oh.
Sir, can you explain it again in a short?
Yeah, the Carnot cycle, as I've written over here, it's a heat engine cycle that consists of these four processes: A to B as I've written down, B to C as I've written down, C to D, and D to A. And then we just applied the formula for each of the processes. Isothermal process, you'll remember. What is the thermodynamics of an isothermal process? Q is equal to W is equal to nRT ln V final by V initial. And
Yes,
delta
sir.
U is zero. Adiabatic process, what is the thermodynamics of it? Q is zero, okay, and delta U plus W is zero. So delta U is minus of W equal to N F by 2R delta T. So here we just need the formula for Q. So this one and this one is used for each of these.
Sir,
About the proof of the last step, that how Q2 minus Q1 comes out to be T2 by, Q2 by Q1 comes out to be T2 by T1. We'll show that in the next step. Just note down up to here. Yeah, you have some doubt?
sir, is there any hypothetical way or theory of or about creating a machine that might be 100% efficient?
So the idea is that there is no hypothetical way also, because next step when we finish Carnot engine, we'll understand that the maximum efficiency that you can have between a heat source and a heat sink is the efficiency that you will have when they are operating in a Carnot cycle. It's not possible to have efficiency of more than what you get in a Carnot cycle. Now in the formula of Carnot cycle, you can see for efficiency to be 100%, you need T2 to be 0. Now 0 Kelvin is not theoretically possible. Rather, it's not practically possible, because 0 Kelvin is that temperature at which molecules should stop moving altogether, and that is not possible physically. So that is a sort of way of empirically proving that the point of second law of thermodynamics, that we cannot have 100% efficiency for a heat engine.
Okay, sir.
Okay.
Sir, but the absolute zero temperature that cannot be even created in the labs.
No, it cannot be created, no, because that's the idea. No? To create absolute zero temperature, you need to absorb all the kinetic energy from molecules so that their motion is absolutely equal to zero. But when you absorb kinetic energy from molecules, that kinetic energy has to go somewhere else, right, to some other form of energy. So can it create a situation where 0 Kelvin will be theoretically possible? No, it will not be possible.
Okay, sir, I got it.
Okay, so it is one of the postulates of physics, one of the laws of physics, that absolute zero is not physically possible.
हो गया सर.
Okay, so finish writing down this part now. Now let's see how we can prove this thing that Q2 by Q1 is equal to T2 by T1. How do we prove this? Okay. So you can see that if you look at the process AB, you have PAVA is equal to PBVB. Okay. And if you look at the process CD, there's also an isotherm. So you have PDVD is equal to PCVC. Okay. So from this, if we divide these two relations, we can see that, or rather from these individually, we can see that VA by VB is equal to PV by PA and VD by VC is equal to PC by PD. Okay, so these are our equations 1 and 2. Okay, now if you look at, so these are isotherms, so we have this. Now similarly, if you look at BC and DA, these are adiabatic processes. So we have PBVB to the power gamma is equal to PCVC to the power gamma, and we have PAVA to the power gamma is equal to PDVD to the power gamma. So if we divide these two equations, okay, so the first two we are not dividing, the first two we are writing directly like this. If we divide these two equations, so we can see that PV by PA into VB by VA to the power gamma is equal to PC by PD into VC by VA to the power gamma. Okay, so this is our third equation. Now in the third equation, if we substitute the result from the first equation here, and we substitute this result from the second equation here, and that gives us that PB upon PA is nothing but VA upon VB. And on the other side, PC upon PD is nothing but VD upon VC. Okay. So we have VB upon VA to the power gamma minus 1 is equal to VC upon VD to the power gamma minus 1, which means that VB by VA is equal to VC by VD. Now, once we have this, then the remaining part, this proof becomes very easy because Q2 by Q1. Now Q2 was, we had seen above, it was mod of QCD. Okay, so it is nRT2 ln of VD by VC's mod. Okay. Now VD by VC is less than 1. So ln of VD by VC is a negative quantity. So therefore, mod of ln of VD by VC will become ln of VC by VD. So therefore, Q2 can be written as nRT2 ln of VC by VD, and likewise Q1 can be written as nRT1 ln of VB by VA. Okay, so now Q2 by Q1, this thing that we are trying to prove. Okay. So first went like this, then we substituted these, we came to this step, then now we are substituting this back over here. So Q2 by Q1 is basically this, it is nRT2 natural log of VC by VD divided by nRT1 natural log of VB by VA. Okay. And now we have this proof that VB by VA is the same thing as VC by VD. So therefore, that becomes T2 by T1. And hence the efficiency, which is 1 minus Q2 by Q1 becomes 1 minus T1. So this is finally proved. Substituting this result over here. This result. That's how we are getting this step. Okay. So this proof is not so important from the JEE point of view. The formula is more important. That efficiency of a Carnot engine is 1 minus T2 by T1. Okay. But the proof is important from your semester exams in college, etc. From that point of view, or your CBSE or HSC exams, whichever type of college or school you are in. From the board point of view, the proof is important. Okay. So while you are writing down this partner, the equation 1, 2, and 3, also refer to the diagram of the cyclic process. Okay. So then you have clarity on, these two processes A, B, and C, D, they are isotherms, whereas the other two processes B, D, and D are adiabats. So their equations are PV to the power gamma is constant, whereas isotherm PV is constant. Okay, so this is about the Carnot engine and efficiency of Carnot engine. Now, so that more or less completes the theory part. Couple of things to discuss as we saw that. So for any type of heat engine operating between a source.
Sir, can we complete this in next lecture?
Sorry, can you better speak louder?
Sir, can we complete this in next lecture as we have lecture after this?
So we have a lecture at 6:50.
At 6:15. Okay, just one last thing you note down. It's done. Okay. So for any type of heat engine operating between a heat source at temperature T1 and a heat sink at temperature T2, the maximum possible efficiency will be equal to 1 minus T2 by T1. That is, the maximum possible efficiency will be for a Carnot cycle between the source and sink. So any other type of heat engine will have an efficiency of less than the Carnot engine. And that's another way of proving the statement of the second law, that the maximum possible efficiency is 1 minus T2 by T1. And in that T2 can never be 0 because 0 Kelvin is not practically possible. So hence the efficiency of a heat engine will always be less than 100%. Therefore,
Prove this in next lecture.
is always less than 100% for any heat engine.
Sure.
Okay, so with this we complete the portion of heat and thermodynamics. Okay. So next lecture we'll again pick up the doubts which are pending from specific heat capacity of gases chapter, and also if anything is pending from calorimetry and previous chapters. Okay, please send the doubts from calorimetry and previous chapters to me by WhatsApp or by message. Okay, so that I can pick that up in the next lecture. And with that we'll finish thermodynamics. The next section we'll do will be heat transfer, which is to do with conduction and radiation. Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending.
Sir, 1 minute. All right.
Bye, sir. Yeah, yes. To answer your question, why the
Sir, 1
Carnot
minute.
engine
Can you
has
show the
maximum
screen?
efficiency? Yeah, I'm showing them. Why the Carnot engine has the maximum efficiency is because in between the processes are involving adiabatic process where there is no dissipation of heat. Because Q is 0 for adiabatic process. No? So any other type of cyclic loop running between T1 and T2 will involve more amount of dissipation of heat.
Hi, sir. Thank you.
Okay.
Sir, just a second. Done, sir. Bye, sir. Thank you, sir.
Okay.